Okay, double checking. All right, so the first thing we'll do today is to take a look at the homework assignment, and I'll give you the solution to the homework assignment first. And then we'll move on to the next homework assignment, which I think is kind of interesting.
Oh, is it the lottery?
This one is more fun than the lottery. This one is very general purpose. You can modify it to do the lottery thing, but all right. So that would be under. Oh, okay. There we go. Resolution improved by contradiction. There we go. All right. So what this homework assignment is about is we start with the CNF that we already have, and I think this one can be. Nope, cannot be simplified any further. This is basically as simplified as it can get. And then the next phase is to prove two theorems. The first theorem that we want to prove, whether you can tell me whether it's true or not, whether it is a theorem or not. But either way, we want to show that that is the case. So the first one is S implies P or Q, and the second one is S implies P and Q. Okay, so we'll work on these one at a time. And as one of your classmates suggested, we can try to use a Google document. So I put in an extra link at the very beginning of this class module list of modules. It's called semester-based share folder, which means this content is supposed to be only usable within this semester, because I kind of changed the way I teach this class just a little bit between semesters, so it may not be as useful for people who are in the next semester. But if you click it, it will bring you to a shared folder, and since I can sign in as the owner of that folder, which I am right now, so I can create any documents in here, and you can open the document as I edit the document in class. Okay, so that can be very handy in a way, because if you need to review something that I talked about at the beginning of the class, you can scroll back on your own laptop or your tablet or your phone without having me to scroll all the way back, and you can ask questions regarding those things. So if I
under more.
Under more?
Yeah. Then scroll down. Go to where is it?
Connect to more apps?
Yeah, maybe it's under connect more apps, because there should be an option for Notepad on there.
So we're looking for Notepad?
Yeah. Because it was under mine. When I went to mine, it was just like you just wanted more, and then there was an option for Google Notepad.
Okay.
Drive Notepad.
That's not from Google though.
Yeah, it's a username.
Sorry?
It's username.
Oh.
GitHub.io.
Okay. Well, GitHub is not bad.
No, actually, I think that was the one I was using. Yeah.
Okay.
Yeah.
All right. Well, we can give it a try. As long as it's free. Since my credit card is not a link to this account. All right. So we'll give it a try. And it's already connected, so we can just start it.
Yeah, it should be.
Okay. So when we say new, more, scroll down to Drive Notepad. Okay. Create and share. There we go.
Yeah, there it is.
Ah.
So it's got the save and everything syntax in the corner.
Interesting. So instead of using a menu, it puts everything down here. So I can select all kinds of different formats. I mean, different syntax, and it can do new line detection. That's only for when I'm reading in a file, I guess. Okay, cool. All right. So let me rename the file first. Okay, so let's see. Where do I rename the file?
I think it's under title.
Probably just click the name.
No, there's a it says title. Title.txt.
Oh,
Yeah.
here?
Yeah, I think. Yeah.
Okay, there we go. So we can rename it to 2017 10/23, I think, today. And since this is only visible from cisp440, I'm not going to name it, with the class name. So this way, when I captured my notes, it is automatically going to be here. That saves you some time. Because now you don't, whatever I type here, is not just recorded in video, but the file itself is already on Google Drive that is shared with you. Okay, so that can be handy. So we'll figure out how we can use this feature throughout this and the rest of this semester. All right, so we'll go back to the homework assignment, and I'm going to do some copy and pasting here. So copy, oops, pasting into a different tab. Try to alt tab it. Okay, so this is basically your psi. Basically, this is the stuff that is already given to you to be true. Okay, so you don't have to prove this part. This is from the previous homework assignment. And what we want to prove, okay, so our phi, this time is this part. So this is the first one. Let's tackle this one first. So we'll do a Control-C, Control-V. Let's see, how do I change the font? Right here. Font size. Okay, I can. Oh, cool. Is that a little better for the people in the back? Cool. Excellent. All right, so, but we don't want to change, S implies P or Q into a CNF. We want to negate it first, okay? So it's very important to remember that we want to add the CNF of the negate theorem to the whole thing before we start any resolution. So now we have to say what is the negation of that. Okay, so we say not phi is really just the negation of S implies P or Q. So now we have to, oh, I like the parentheses matching. That's very handy for this sort of thing. All right, so we'll first deal with S implies P or Q, using the definition of implication. So it becomes the negation of S or whatever is on the other side. So that's what it becomes. And this one is relatively easy to deal with. So at this point, one thing we can do is to dissolve the parentheses, the inner parentheses, because disjunction itself is associative. So it doesn't really matter whether we put the extra parentheses or not. So it's not S or P or Q, just like that. And then you can apply De Morgan's law to this entire thing. De Morgan's law is really about distributing an outside negation into the inside, and then we are turning all the disjunction in the inside to conjunctions, or the other way around. So it's a very useful type of transformation. So in this case, it becomes not S. Okay, we'll cancel out that stuff later on. Not P and not Q, because it's distributing the negation to the inside. And now we can do the simplification. Becomes just S, not P, not Q, which by itself is a CNF. Yep.
For this theorem, if you turned it into a CNF first, it took like 2 steps to negate it instead of 5.
Oh, you mean turn phi itself into CNF first?
If you turn that into CNF first, then it takes like 1 step to turn it into a negated version of itself. Instead of the 5.
Okay. But this is just using the full steps that I talked about in class.
Oh, in class you said to negate it, then turn it into a CNF?
Yeah. Mm-hmm. Well, basically what we want is this part. So as long as you can get to the same point, it will still be okay. Yep. Now, if you don't like this because it doesn't look like CNF, you can always convince yourself that it is a CNF. So it's S plus 0, not P or 0, not Q or 0. Okay? Because anything or 0 doesn't change the original meaning. So now what we want to do is to combine the two. So now we have psi and phi, not phi, sorry. So I'll put an explicit and here because otherwise it's not very clear. So we want to look at psi and not phi. Remember, psi is what is given to you to be assumed to be true, so you don't question that part. Phi is what we're trying to prove. So when you combine the two, if phi in fact is a theorem, we should be able to resolve to false. In other words, we should be able to arrive at contradiction. So we'll now take a look at this part here. So this really just becomes a concatenation of all of this stuff and this stuff here. Okay. And let's see, can I hide this one? Probably the,
I think when you clicked on the name before, it minimized it, right? It made it
yeah,
smaller.
it makes it smaller. Okay, that's fine. Okay, all right, so now we look at this kind of long CNF, and then we want to ask the question, is there any way to resolve this? Well, what you want to do is to resolve, since we have Q here, and it's on its own, so okay, the more systematic way to do it is to look at the first one, and then you say, okay, what can it resolve with? It cannot resolve with the second one, cannot resolve with the third, cannot resolve with this one, cannot resolve with this, but it can resolve with this. Or, okay, just sequentially, it will resolve with this one first. So I'm going to do a very, very systematic way, which may not seem to be the smartest one, but the computer will do it this way. Okay, so we resolve these two, and after the resolution, we keep everything that we already have. But then we can also add the one thing that we are resolving, which in this case is just P or 0. Okay, the P is coming from here, and then the 0 is coming from here. The not S on this side cancels out this S on the other side. They are used for the concatenation. Yep, question?
The resolution, you're not eliminating terms, you're creating more terms.
It creates more terms. Yep, and all the terms that you create can be added to the conjunction without changing the meaning of the conjunction.
Okay.
Yep, go ahead.
You already could have canceled out the Q for 0 and
Yeah.
now Q for 0.
Say again?
You can already cancel out the Q.
Oh, okay, that's right. Okay, it's already here. But I'm doing it very systematically. In other words, I'm just looking at the first one and see what it can resolve with. So, yeah. So I'm just doing it in a very dumb way where your program is likely to do.
I wouldn't say dumb because I only figured that because Q is the first term in mine.
Right. But your program, will typically do it like this, sequentially going through, the first term and cross it with any other term and find out, hey, these two can resolve too. So after these two resolve, then you get, not S or 0, which is not previously in the pool. Okay. Now you can probably see that there are many ways to resolve to false already, but I'm still going to do it, kind of very, very mechanical way. So I look at the first one, which is this one here, and continue to look. Okay. Cannot resolve with this. And cannot resolve with this because this is the one that we just added. Yep.
For our answer that we turned in, did we have to have every single resolve?
Nope.
Expressed? Okay.
Nope, you do not. Yeah, so you guys don't have to do it the same way that I do. But then in the second one, I've got to look at this term and see what it can resolve with. So we can resolve this one with this one. We can resolve it with, yep, that's the only one I think. Sorry?
You could have done not S and S
Not S and S.
on the first one.
Remember, but I'm trying to do it in a very, very, very mechanical way. So the very mechanical way is to look at this one and say, okay, we are moving on to this one because we're done with the first. So we can look at this and go like, it can resolve with this. Okay, when these two resolve, so we kind of copy and paste the whole thing, which is really tedious. But this time we get not T or 0. Okay, and you can see that we have so many ways to get to contradiction already, but then we systematically look at this one and look at this, cannot resolve, cannot resolve, cannot resolve. Then we look at this one. We move on to the third one, and then we sequentially go through the third one with the rest. In other words, what we do, or what your computer program is going to do, is look at this one and go like, okay, what can this resolve with? Cannot resolve with the one right next to it, cannot resolve with this one, cannot resolve with this one, cannot resolve with this one, can resolve with this one. So mechanically speaking, this is the time when we actually resolve the whole thing to a 0 or 0. Is that making any sense? Okay. Now you can get to the contradiction a lot faster than this. Okay, that's because you are running an algorithm called the eyeball algorithm, because you can just eyeball and scan the whole thing and go like, oh, I can pick out this one, I can pick out this one, done. Okay, But when you're writing a program to do this, your program is unlikely to be able to scan through things just like you do. So instead of doing that, we'll just mechanically pick the first term out of the entire CNF and just go like, okay, can you resolve with this one? Nope. Move on to the next one. Move on to the next one, and so on. Yep. Go ahead.
Shouldn't you actually only check the first term of the CNF against the thing you just concatenated with the?
Yep.
Because if you're just looking at your psi, you could if your psi was already able to resolve the 0, then you wouldn't be adding. Or
Correct.
You would be adding. It would just be 0 added.
Right.
Not phi. So you should look against. You should look at psi against phi, right? Initially. Or psi against not phi initially.
Psi and not phi.
Yeah, but I'm saying you should look at the terms of
You mean look at
psi
these?
against not phi initially. Otherwise, there's no reason to check psi against psi, right? Initially.
Psi and psi.
The first term.
The first terms, the initial terms. There's no
You're
reason to
checking
check
them against the
psi
second
terms
term.
against the psi terms.
Try to resolve it against itself, you mean?
You mean resolve amongst these three?
No, the psi. Or phi.
Phi?
Psi.
Psi.
Sci-fi.
You mean here?
There's no, yeah.
You
So
check everything in
there's
psi.
no reason to check the first one against any of those in the CNF.
That is correct.
Yeah.
Yep. But as a simplified algorithm, you just look at everything. So yes. So given the context, this is given to be true. Then you don't. These 5 terms cannot have a contradiction on its own. Correct. Yep. All right. So is that okay so far? All right. So the next one is. So I'm just going to go back here, but this time we have a different phi. Okay. Same psi. But this time phi is just PQ, so the way we negate it is a little bit different. So we say not phi is the negation of S implies PQ, P and Q, and that becomes the negation of not S or PQ. That's using the definition of implication. And now we can apply De Morgan's law. So De Morgan's law says this becomes not S and not PQ. But this not PQ is not okay because this negation is applying to a conjunction, so that's not okay. So we have to apply De Morgan's law one more time. This becomes S, and then we apply De Morgan's law, so this becomes not P or not Q. And then we use distribution so that no, this is already done. Yep, it's correct. This is already in CNF, and we just have to make it look like CNF. Like so. Okay. So now we make one long concatenation, or one long CNF, which is psi and not phi. So that's just going to be copy and pasting this with that. All right, and now we can start the resolution. So this time I'll use Jake's suggestion because basically the first 5 terms cannot contain a contradiction. So we will compare the first term with the 6th term. So we look at this term and go like, can we resolve with this one? Yep, we can. All right, so we will resolve that. So we'll take this one, we'll take this one, and then have these 2 resolve. But the point is, this is really mechanical. It's really just about matching patterns. So now we have P or 0. But if I want to stick with the really mechanical aspect, now we pick the second one, and we ask, what can this resolve with? Okay, so we can take this one. And did I miss something? Yep, I did. Actually, I missed this one. There's one more thing this one can resolve with. It's not particularly really helpful here, but it can be resolved. So we'll pick up this one. I'm trying to make it as mechanical as possible. So this time we are left with not S from this one and not Q from this one. So this is becoming not Q or not S. There we go. So we are now done with the first term. Now we move on to the second term. So the second term is P or not T. So once again, we move past the 5th term because that's guaranteed not to have a resolution. And then we've arrived to the same term here, and we can resolve with this one. Now, obviously, in your homework, you don't have to do it this way, but I'm just showing you, mechanically what you can do. Okay, so we have that. And that should be all that we can resolve with. So now we move on to Q. Yep, go ahead.
I think it would be better for it to have it check against itself just in case one of the term resolutions was missed in the original.
Well, in that case, that means whatever you're told to be true is not true. It contains a self-contradiction.
Or well, I mean, like it might still be true, but it's just not completely expanded. Like it's not all the way resolved.
But if we resolve to 0, that means it is already false. You're just discovering that it is a contradiction.
Well, I'm saying like maybe you needed a not P plus S in order to get a not S and an S to cancel so that you could get what you needed to get in order to get the resolution. Like, but the term wasn't there.
Okay, so you're talking about these 5 terms. We should try to resolve these just to make sure there's no 0 in here.
Just to make sure that there's no missing terms that you might want to use.
The only reason why you want to resolve amongst these 5 is because this can be false. But if this is false to begin with, then it is not a truth that you can start with. So it's it's not necessary, but if you do it, it doesn't hurt anything because this is guaranteed not to resolve to false. Okay, so we move on to this one. We can definitely resolve with this. Okay, so when these 2 resolves, we get plus 0 from the first one, and then we get not P from the other one, like so. And of course, you can already tell that it's resolvable between this and this. But mechanically, we're not going to do that. Okay, so we're going to do it really the long way. And I probably want to zoom out just a little bit. Okay, we look at font size, change. Okay, that might be a little better. Okay, so now we are still looking at this Q here. So mechanically, it can also resolve with 2 other terms, which is down here. One is down here. So we look at the result of that resolution. We pick up the plus 0 on one side and not S on the other side, just like that. And there's one more before we can move on. So there's one more down here. Okay. It's tedious if you're doing it mechanically, but since the computer is going to do it, it doesn't really bother you because you're just writing the program to do it. Okay, so now we are done with the Q plus 0. We're moving on to the not R or not S. That can be resolved with this S over here. That's the only thing you can resolve with. Okay, but I think at this point you guys are getting pretty bored already. But you're also getting the idea of how to do it mechanically. So if you do it mechanically, it really is just kind of like a nested for loop. Okay, at least in concept. You have the outer for loop controlling which one is the first one that you're looking at, and then you're using the second and nested loop to look at the rest of the conjunction. So this way you look at every single way to pair up the sub-expressions, and if you can resolve, you add it to the end, and then you just keep doing it until one of 2 things happens. One, you cannot add any new terms anymore, okay? Because whatever you resolve to is already in here. Or 2, you have a 0 plus 0. You have contradiction. So in this case, I'm just going to shortcut the whole thing and just pick out, I have many ways to do it. There's S plus 0 here, and then there's also not S plus 0 here. So they can resolve to false. No. Okay. Control C, Control V. So now we have 0 plus 0, and so it is a theorem as well. So both of those are theorems. The first one, easy to prove, because you just have one single resolution. This one, I think, is a little bit has a few more steps. Yep.
So when you say it's a theorem, are you saying that the statement is consistent with the original statement?
It is implied by the original statement. So what I'm saying is this implies this. Okay, back there, and then you. Yep.
On the homework, if with each resolution step we didn't keep on writing all of the terms, but we got to the correct conclusion, is that still all right?
Yeah.
Okay.
Yep. Go ahead.
So on the not phi, could you have distributed the last term?
You mean this one?
Yeah.
Well, if you distribute, it becomes S naught P or S naught Q, but that is not a CNF. This is already in CNF.
You can do that and then distribute again.
Yes.
And then you come up, that's what I did, and I came up with four terms, but it still worked.
Yep. So we can do it that way too. Yep. Having the shortest path to the answer is not important to us. We just want to get to the correct answer. Yep. Are there any questions? Yep.
So, why is it that after you find the first zero or zero, that like you kind of know it's going to
Something and zero.
You mean why we know at this point that the theorem is a theorem? The proposed theorem is in fact a theorem?
Yes, but like earlier on, without doing everything, because you said, oh, this one will probably be like resolved to zero.
Because over here, you can tell early on, earlier that we already have a P here and a not P here. So at this point, I could have resolved it to zero already. There might be a shorter path to resolve it to zero. I just did not choose the shortest path to do it. I chose to do it very mechanically just to illustrate that that's basically the whole point of using CNF. Okay, so the whole point of using CNF is to enable us to use resolution. But we also proved that in your homework assignment in the previous one, we also showed that you can give me any Boolean expression that is valid, and we can always turn it into CNF because that's important. And then the second thing is with CNF we can perform resolution. Now resolution itself is really just saying, okay, there's a mechanism here to add new terms without changing the meaning of the entire conjunction. Okay, that's all it does. So by itself it's not very useful. But when you combine that with proof by contradiction, it means now you can attach the negation of the theorem that you're trying to prove as a CNF to the original CNF, which is representing everything that you are told to be true. So when you attach those two together, then you get psi and not phi. Phi being the theorem that you want to prove, and psi being everything that is known to be true to begin with. And proof by contradiction says if phi in fact is a theorem, the conjunction between these two, phi and not psi, should be a contradiction should be false. And that's what resolution is doing for us here. Is we want to eventually resolve to 0 plus 0, which means okay, the whole thing is false, but what does that mean? It means proof by contradiction itself is successful, and that means phi in fact is a theorem. So is that helping? Yeah. It's combining a lot of different things in order to make it work. Now, so getting back to the point of why did I do it in a very mechanical way? Because the whole idea is we want to make this so that a computer can do it easily. So you can write a program to do it. And you can see at this point it is actually doable using a computer, using a program. If you don't mind, using kind of wasting, resources a little bit, you can do this with a C++ program, pretty easily.
Wasting resources.
Huh? Yep. You just you can use either a linked list or even an array to represent each sub-expression. And if you want the most optimal way to represent these things, it might be a little bit more tricky. If you only have like 4 kilobytes of RAM, entire program space, that might get a little tricky. But if you have like 4 4 gigabytes of RAM already in the system, this can be done in a variety of ways. Yep, go ahead.
Like just questions. You say that this implementation can be done using array and using nested loop. So like double loop. I was wondering, like, how does the double loop keep on track of the dynamic and the size of the array? Because each time you result in resolution, your size increased by 1.
You can always, do the not so optimal way. Every time you add a term. So there are two important points. One is every time you add something, you have to make sure it's not already in the CNF. Okay, and then the second one is you can always just go all the way back to the beginning. Oh, okay. A gentle reminder.
Just right next to it.
Yeah, just initial next to what you have already there. Okay, so the idea is, if you add something to it, you can always start from scratch. Okay, it doesn't really hurt, but you can also compare to the end of the entire CNF. So your double loop is not ending, with a fixed index. You're ending with the last term of the entire thing. Is that okay? Yep. All right. Any other questions? No other questions? Okay. So if there are no other questions, I think we answered the question of, how bad can this be, right? How many terms can we possibly end up with? Is it finite? So there are two questions. The first question is it finite? And if it is finite, how big can this number be? And we came up with a number that pretty much it has to be the absolute maximum. And to illustrate that, I'm going to use my document camera. There we go. Capture device, play. And it's pretty much in focus already. I'm impressed. Okay, so let's say you have PQRST. PQRST, 5 variables. P can be missing, so I'm going to use a box to say it's missing. P can be just P by itself. P can be negated. So we have 3 choices for P. What about Q? 3 choices, right? R, same way, can be missing, can be non-negated, can be negated. Same thing here. Okay, you can see it's absolutely boring to look at this, right? Then you go like, okay, so now we look at this, and we are looking at, this is a set notation in a vertical way. Cartesian product with this one. 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 So that would give you, that's going to give you what? It's going to be 3 to the power of 5. But that would give you absolutely every possible sub-expression that you can have. Is that making any sense? Yep.
So it's the number of possibilities times the amount of, or to the power of the amount of variables?
It's 3 to the power of the number of variables.
So 3 is the amount of possibilities we have?
Right. 3 is the number of possibilities because, in each sub-expression, a particular variable can be missing. It doesn't make a difference. It can be non-negated. It can be negated. So those are the only 3 choices you have. So if you don't like the square here, you can always put a 0. No, it's just false. But you can.
That's true.
Yep. So it's just false. So now so whatever output is out of this entire Cartesian product would be the all the subterms that you can have, all the disjunctions within the CNF. So we have in this case if you're only interested in the cardinality of this entire thing, then we are looking at 3 to the power of 5 in this case. So it's 3 times 3 times 3 times 3 times 3. Yep.
For it to be a true statement,
I don't care. I just need the upper bound. Because to me, what is important is to make sure that there's an upper bound, and I know how long the algorithm may take in order to make a conclusion. Because the conclusion can be, I get to 0 plus 0, which means A, the theorem that you're proposing is actually true. Or we can get to a point where the algorithm says, I have tried every single way of resolving, and I'm not able to add any new terms to the CNF. Then you just quit. You go like, okay, whatever you propose to be a theorem is not a theorem. Done. Is that okay? Yep.
But if only half of them can be true, then wouldn't it be like it should find that it's true or false by
But
that
why do you
time?
know only half of those can be true?
Because, well, I'm not saying half, but like it's either there, not there, or false. So there is a limited number of like a lot of the combinations within 3 to the 5th would be self-contradictory. I mean, like it would contradict with previous ones.
Yes.
So then, like your program should finish running before it could ever get anywhere near 3 to the 5th.
That is true. But the bottom line is it is finite. That's the bottom line. I just need to know it is finite and the algorithm will terminate. And this is a sharp contrast compared to general propositional logic, where you can go in the wrong direction and keep deriving useless but valid, well-formed formulae. So in that case, you can just keep going and going, and you can spend years in an algorithm and not know whether the theorem is not a theorem or just that you haven't gotten into it yet. Yep.
Any idea where our next test is?
About week 12. Which week are we in right now? 10?
I think it's 10.
Okay, so next week we're going to have a practice test, and then the week after that we'll have the actual test. Yep. All right. So are we doing okay so far with this homework assignment, and also what it is representing, because that's kind of important too. Okay. Because go ahead.
So why would it be infinite in the other propositional logic?
Oh, okay. So why would it be infinite? Well, the space itself is infinite. Okay. This is the space. Okay. When you look at this part here, this entire set, that's the entire space of your well-formed formulae. Okay. Your entire space only has, in this case, 3 to the power of 5, which is what? What is 3 to the power of 5?
243.
243? Okay. 243. So if your entire space is finite, it cannot take you forever to find the solution. So when you look at the other one, okay, so when you look at normal propositional logic, well-formed formulae space, okay, WFF space, it's infinitely large. It's infinitely large without even knowing what is in your iota. Because we know that if P is a variable in alpha, then we know P or not P is in that space. It's guaranteed to be true, right? But that means P or not P or not P or not P is also guaranteed to be true. Then you take this and then you apply the same trick to it. So you can keep going in this direction without moving an inch closer to what you're actually trying to do. So this space is infinitely large, and with a space that is infinitely large, it is difficult to come to the conclusion that, the theorem that we are really trying to prove is not a theorem. You cannot make that conclusion easily. Remember the haystack and the needle example that I was using in the previous class? If your haystack is infinitely large, and I ask you whether there's a needle in the haystack or not, it is impossible to answer that question, because it is always possible that the needle is somewhere that you have not searched yet, as opposed to a haystack that has a known size. Okay, it's only so big, so if the needle is in it, it has to be within this space. All right. Okay, is that okay? All right. All right, so if this is okay, we're going to switch back to the notes, and we'll start with your next homework assignment. I think I'll describe the homework assignment first, and then we'll go back and revisit the terms if necessary. So it is your omega generator. Sounds like an Autobot kind of thing. Okay, you guys are way too young to know what is Omega Supreme. No, see, I can see all the blank faces like, what? Omega what? It's one of the Autobots. It's the Gen 1 Autobot thing, so the movies that you watch now has nothing like that. So in this case, in this particular homework assignment, I want you to write a program. Okay, you can do it in C, C++, or Java. And I think based on the prerequisites of this class, you guys should know at least one of the 3 programming languages.
You can't use Python?
Well, if I can run it in Linux, you can submit it. You can do it in Python, PHP, Perl.
You can do it in assembly.
You can do it in assembly.
You do it in Haskell? Not in Haskell?
Haskell?
Ruby?
What is that?
The program, the function, never mind.
Oh.
Oh.
Okay, so this is what the program needs to do. The first thing is it has to read from standard input, which is known as cin or stdin, depending on whether you're dealing with C or C++. So there are 3 numbers you have to read. The first number is a base 10 number. You can assume all of these numbers are unsigned, so there won't be any negative numbers here. So the first number is the number of choices for the first trial. Okay, in the case of lottery, for Powerball, lottery, this number is going to be 69. But as you see later, we have a constraint of not running up to 69. The second number is controlling the number of trials per experiment. Okay, so we can look at those terms later on. So in the case of lottery, each drawing of a ball is called a trial. So with Powerball, there are 5 trials to each experiment because you're picking up 5 balls out of 69. The third number is not really exactly a number, it's just Boolean. It's just either 0 or non-zero. If the third number is 0, that means we are running those trials without replacement. Whatever you choose in an earlier trial of an experiment, you cannot use it again. So that would be the case of lottery. Okay, you pick up a number, that number can no longer be picked again in later trials. If this number is a non-zero, it means it is with replacement. When it is with replacement, that means every single trial has exactly the same choices. Is that okay? All right. Now, for the output, the choices that you choose for each experiment or each possible outcome of an experiment is represented by a lowercase English letter. This means the number of choices for the first trial can range from 1 to 26, because we only got 26 lowercase letters. If the experiment is without replacement, the number of choices of the first trial has to be greater than or equal to the number of trials per experiment, because otherwise it doesn't make sense. You won't have anything left for the later trials. Does that make any sense? So if you only have 4 choices for the first trial, and I say, okay, if each experiment has 5 trials but without replacement, the first 4 trials out of the 5 would have used up all the choices already. Your 5th trial will have nothing left. That doesn't make any sense. Okay? So that's why we have this constraint here. The output should be organized in lines. Each line represents a possible experiment outcome. Each line contains lowercase English letters. Use space as a separator. So I got some examples here. 3, 2, and 0 as input. So that means the first trial in an experiment has 3 choices, A, B, and C. We are only conducting 2 trials per experiment. And 0 means it is without replacement. So your output is going to look like something like this. The ordering may not be like this depending on your algorithm. So when we have chosen A to be the first trial, then we only have B, C left for the second trial. If we choose to use B as the first trial, then we only have A, C left for the second trial. If we choose to use C in the first trial, then we only have A, B left for the second trial. Is that okay? Yep.
So they can only have up to 26 choices.
Yes, that's what the description said a little bit earlier.
So like you can't do the lottery thing because everything.
That's correct. Yep. That because it has 69 choices. But the idea would still be the same. Okay, keep on going. Here's another example, 2, 3, 1. So this means we have 2 choices for the first trial, but since this is with replacement, that means we have the same 2 choices for every single trial in an experiment. There are 3 trials per experiment, so now we have kind of like a truth table, AAA, AAB, ABA, ABB, BAA, BAB, BBA, BBB. Is that okay?
This would be so easy in a functional language. This is like it'd be really easy in a functional language.
Yeah, you are correct. It is very easy in a functional language, or if you do this in a recursive way, it is also pretty easy.
Is that why you made the? Is that why you made the number 26 instead of 69 because of recursion?
Well, it's just because I choose to use English letters for each choice.
That's a good point.
Yep. So are there any questions about this homework assignment? The program must be done in C, C++, or Java, but if you have a particular programming language that you want to use, ask me first, okay? If you want to use Python, it's okay. Perl, okay, with Python you have to tell me which version. Because 2.7 and 3 are different. You can do it in PHP if you want to. I mean, there's no reason why you cannot do this in PHP. There's no, huh?
Terrible idea.
Well, PHP is not locked in to generate HTML, code. It can generate anything you want, right? Yep.
For choices, it was the number of letters that are able to be represented. For just to clarify,
The first number?
the first number is choices, which is the number of characters that are able to be represented.
Starting with A, yep.
Starting with it.
Always starting with A,
Right.
yep. Yep.
So I'm still a little confused when, like on the second example, when you have one on the last term, like what is that? You said with replace or without, like what does that mean?
Okay, so let's go ahead and take a look at some notes here. So let's go to the modules. And let's see, we are, okay, maybe in this one, maybe in this one too. I cannot remember which one. Okay, we'll take a look. We'll take a look at counting first. Trial, experiments, and outcomes. General counting. So this one does talk about without replacement. So without replacement means if an earlier trial has used up a particular choice already, then that choice is no longer available to all later trials in the same experiment. Like in lottery, that is the case.
So like if they in that example you had 3 trials per experiment, right? So after that experiment you can use it again.
So you can reuse it, but the next experiment begins with the same 3 choices again.
Okay.
But so basically the without replacement concept applies to trials of the same experiment. But the cross experiments, every time you start an experiment, the first trial always start with 3 choices in that case, A, B, and C. Okay. All right. So here's a an idea for you guys to get started with your homework assignment. Okay. If you scroll all the way down to look at the outcome set of experiments without replacement, because with replacement it's easier. Because you don't have to keep track of what is already used. So you just have to say, okay, we'll go through all of these, and then for each one, we'll recursively call the same subroutine and say that, okay, we have one fewer trial to deal with now, go deal with it, right? But without replacement, it's a little bit harder. So the question is, how do we generate the outcome set when we have to deal without replacement? So I come up with this notation here. So let's say T represents the pool or all the choices originally presented, which is the same thing as what is available to the first trial. So T represents the set of all the choices for the first trial. And then we use omega I in parentheses T to represent the outcome set of an experiment involving I trials. So this I, subscript I, represents how many trials we are dealing with. and T is the initial set for trial 1 or trial 0, the first trial. So by definition, you can see how omega 1 T is just T, because you have one single trial of the entire experiment, and I ask you, what are the outcomes? Well, whatever the choices are to begin with. Is that okay? All right. So now the next question is, what about omega 2? In other words, I want 2 trials, but we want to start off with T. So omega 2 T, okay, is going to be, the big U is just saying that it's a union of, for each E in T, we want to perform that union. Okay. So for each T, for each E element of T, we want to come up with a tuple or a Cartesian product that looks like this. So the highlighted portion here, let me magnify this a little bit. So the highlighted portion here is doing a Cartesian product, which doesn't seem very useful, because what it is doing is the first set of the Cartesian product is a singleton set, which only consists of E as the element. But it's crossing with a subset of T, because the second set, or the second portion of the Cartesian product, is T, which is what you're given with, minus the set containing E. Does that make any sense? Because we used up T in the first trial already. So for the second trial, you have everything except for E available to you. So this particular Cartesian product represents all the possible outcomes when E, whatever E is chosen as the outcome of the first trial, and then the rest is just done like that. Is that okay? But how many Cartesian products can we have that looks like this? Well, it depends on how many elements you have in T to begin with. If T has ABC, then each one of those elements can serve as this E. Is that okay? Yep, absolutely. So I have to copy this a little bit. Oh, I can do it. I can do a dual display here. This is super high tech. It doesn't get any high tech than this. Yep, here we go. Right there. Okay, so let's say T starts off with A, B, C. Okay, I'm using this also because it coincides with the first example of your homework assignment. Okay? So T is ABC, okay, which means for the first trial of an experiment, you have A, B, and C to choose from. So in this case, omega 2 is going to be the element A in a set times T minus E, so that would be BC, right? Does that make any sense? When I choose A to be E, this fits the bill. So now we have a union with, what if I pick B as E? Well, then B will be the choice of the first trial, and then we have AC left for the second trial, and then we have another union here. What if we pick C as the outcome of the first trial? Then we have AB left for the second trial. But what is that? Let's work this out. So the first set, okay, this one boils down to AB as a 2-tuple, AC as a 2-tuple. Is that okay? Because it's a Cartesian product. You pick one thing out of the first set and one thing out of the second set, join those two with a tuple notation, and that's one element. Is that okay? Mm-hmm. So then we look at the second one. Okay. It starts with B, and with A, starts with B, and with C. And the third one here is CA and CB. But we are making a union out of these, which means, yep, go ahead.
So the second number on the program is the number of trials we're performing?
Yes, that's
So
correct.
how isn't this 3 trials?
Nope, this is 2 trials.
3
It's 2.
choices.
Oh, okay, okay.
Yeah. Yeah, this is only 2 trials.
So if it were 1 trial, it's just AB?
If it's 1 trial,
Just do 1 count.
omega 1 of t is just t by definition. If you only have 1 trial, and t represents all the possible choices of the first or the 1 trial, then you get everything in t back. Yep.
That last tuple, should it be CC or CA?
It's CACB because it's crossing A and B here. So A and P can be chosen as the second. Is that okay? So when you perform the actual union, then you get back, you know, what you saw earlier on the screen. You're just basically looking at everything here. Because the subsets do not intersect at all, so when you look at the union, it really is just copying everything down. So that becomes the actual, the set of all possible outcomes, but for the experiment. The experiment of 2 trials in this case. Have we seen this before? We have seen AB, AC, BA, BC, CA, CB on separate lines. That's the output of your program. Is that okay? Yep.
So essentially, we're turning this into a function in our program.
Yep.
Okay.
Yep. But there's more.
And this is without replacement, right?
Huh?
This.
Say that one more time.
What you just wrote is without replacement?
Is without replacement, correct. With replacement, it is, you don't have the restriction, so you have AA, AB, AC, BA, BB, BC, CA, CB, CC. So that would be the easy one. That's easy to track. Because you don't have to. So basically with replacement is to take out this term. So it becomes just a straight Cartesian product. But without replacement means you have to take out something first, so it's much harder to express the actual set of all possible outcome for the experiment. Yep.
So with replacement, we can have duplicate values. I mean, we will have it.
With replacement?
Yeah, with replacement, we'll have duplicate values. Like
yes.
Like A, B,
yep.
A.
Yep, exactly. All right, so the recursive way to define this, okay, is omega IT, which means, you know, an experiment involving I trials, and the first trial has T as a set of all the choices, is going to be the big U, or the union of the following. And this part we know already. For each element in T, we will use it as the first item in a 2-tuple. But then the second one is now recursive. Basically, we have 1 fewer trial, okay? And at the same time, we also have 1 fewer elements to choose from for the first trial of the sub-experiment. Is that okay? So this is actually, in a way, telling you how to implement your program. It is telling you how the recursive relationship occurs in your program. And yes, you can do recursion in assembly language too. Yep.
Order matters.
You should do it in assembly.
Order matters.
That's enough.
Order does matter. Yep. So ABC is considered distinct from CBA. Yep.
Can
Is
you
that okay?
highlight it? I'm having trouble reading it.
Mm-hmm.
Can you click so it's not highlighted?
Oh, okay.
I just can't read it. Okay, thank you.
Well, this is already in Canvas, so you don't have to actually write it down. Yep.
So in the example that you showed with the document camera, what if it was 3 trials? How would that work?
If it
3
3 trials? Okay, so we'll give it a try. Okay. So we'll keep this one up. Okay, keep the recursive definition up. And okay, there we go. So we have a fairly large area here for the actual documentation, for the actual stuff. So we are looking at omega 3, and the initial set would be ABC, right? You still want to start with ABC?
Yeah.
Okay. So then you just write it out as A cross with omega 2, and we only got BC left. And then we union with B in its own set, Cartesian product with omega 2, and at this time we have AC left as the choices, union with C in its own set, Cartesian product with omega 2, and this time we got A, B left as choices. Okay? Then you have to work out each one individually, okay, because that's the whole idea of recursion. So now you look at omega 2 with A, B, C. I'm not going to work out the entire thing, but you will probably get the idea. So BC, omega 2 BC is going to be B on its own as a set, Cartesian product with omega 1 C. But that is just, C all by itself, because omega 1 is just the set itself. Okay? And then union with C, which is the other element of the original set, times omega 1, and then once you have U sub C, B is the only left. But that is just the set of B itself. So when you look at this, it is BC as a 2-tuple in one set, union with CB as the result of the second Cartesian product. So this entire thing is really just BC as one 2-tuple and CB as the other 2-tuple. Then you take this and you put it back here to do the Cartesian product. So the first line here, just to work out the entire thing here. So this whole thing works out to be A, B, C as one 3-tuple, and A, C, B as the second 3-tuple. Is that okay?
Our output, do you want us to store or just display it?
Just display. Your program should not need a whole lot of storage, because if you're doing it recursively, what you need to, so the first thing you need to do is to have some way of representing a set. Like, have I used this already? So that's the first thing you need to figure out, is how do I represent, have I used up one, this particular letter out of the 26? So how you want to represent it is entirely up to you. There are several ways that I can think of, to do that representation. One way you can represent it is you use a bitmap representation. So when you use a 32-bit integer, U and 32 underscore T, if you do a pound include first, include stdint.h, standard integer.h, that would give you all the type defs, given a certain width of integers. But since we already know that each set can only be representing A to Z, a 32-bit integer is more than sufficient, right? So now we can say, you can use a 32-bit integer as a set. So we'll use S1 as a set and S2 as a different set, like that. And the way you store a particular element into the set to add an element to the set is to say S1 or equal to, this is a bitwise OR, and then you have to say, okay, what element are we talking about? Oops, sorry. It's one left shifted by the element that you're talking about. Now in this case, this element can only go from 0 to 25 based on the limitation of this program. So how do you turn lowercase a to a 0 and lowercase z to 25? I will leave that up to your imagination. The only clue that I'm going to give you is the ASCII code of A, lowercase a, to the ASCII code of Z is contiguous, which means it doesn't skip anything in between. Yep.
Would it still work if you use the ASCII version of 0?
Huh?
Would it still work if you use the
Minus
ASCII
0.
version of 0?
You convert it into a chart.
You have to. There's a conversion. So internally, using this representation, internally, lowercase a is 0, lowercase b is 1, and so on. But when you print it out, you have to print it out as lowercase a, lowercase b, all the way up to lowercase z. But internally, you can track everything just by numbers. They don't have to be represented as characters. Yep.
So we could have it as numbers until the very end and then just convert them back to the
Yep.
form. Okay.
Yep, exactly. Okay, so how do you know whether a particular element is in a set or not? This is how you add an element to a set. To test whether an element is already in a set, you say this, whatever element it is. So this is a bitwise AND. So with a bitwise AND, you are basically masking a single bit out of 32 bits and say, okay, is that bit a 1 or 0? Okay, so that's one way to represent a set. Okay, how do you make it empty set? How do you make S1 empty? Cannot be any easier. Because then all the bits within the 32-bit integer are all zeros. You're zeroing everything at the same time. Is that okay? How do you set all the elements, like all 26 elements in the set, without going through a loop and all the shifting and stuff like that? Okay, so 26 is, okay, I'm looking at 0x, okay, 4, 8, 12, 16, 20, 24, 26. So this is how you initialize a set so that all the elements from 0 to 25 are set.
What's unit 32T?
Unit unsigned integer 32 bits.
You don't have to use it this way, okay? I'm just giving you a particular way to do it. You can use the template class called set in C++. If you know how to use it. If you don't, you can look it up. But this is just one of many ways to represent a set. I personally like this because it's very compact. Okay, it doesn't use up a lot of memory. It's bitmapped. It's really efficient. Is that okay so far? Okay. So we have, so this is to add an element. This is for checking an element. This is initializing to an empty set. This is initializing to the set that has 0 to 25 as elements in the set already. Basically, each bit in the 32-bit integer represents the presence or the absence of an element. Is that okay? And the difference between with and without replacement is whether you do this subtraction or not. Which means if you know how to do this program without replacement, the version with replacement is easy peasy. Because you just say, okay, let's not subtract that element that we have chosen. Is that okay? All right. So I'm going to leave this up to you guys, okay, to kind of think about how to do it. You have 1 week to do it. I think that should be enough. Okay. Yeah, exactly. As long as you don't procrastinate until the last few minutes.
Procrastinate the last few minutes?
Yep. If you do this in Prolog, you probably can get it done in a few minutes. Or if you know any scripting language, it's not difficult to do with certain types of programming languages. C and C++ may not be the most well-suited language to do it, but if you use the bitmap method, it's not too bad. You just have to define a bunch of sub-functions first to deal with set operations. Then the rest is actually pretty easy. The set operations that you need to perform are what? Okay.
Cartesian product.
Hmm?
Cartesian product.
Well, the Cartesian product, interestingly, is not one of those actual explicit operations you have to perform. The union is, okay? So you have to find a way to, quote-unquote, do union. Well, the union, I take it back. This union is not even one of those. This one is. So the subtraction and also the initialization of the set to all the elements, those are the only two actual things that you really have to do, and also to test which element is in the set that you need as well. Is that okay? Sort of? But this is going to be done recursively, so you kind of have to think about this and go like, okay, what are the parameters to the recursive subroutine, and what it is supposed to do in a subroutine? So that's kind of what you have to think about. Is that okay? So the worst case scenario I can give you is to give you 26 as the first number, and then some big number as the second number, and then a 1 for the third number with replacement. Yep.
This isn't really about the homework, but can you explain your hex and how that's 25? For some reason I can't.
Okay.
How that's 25.
Okay, remember we're using 1 bit to represent the presence or the absence of each element, right?
Okay.
And for the sake of this argument, instead of saying element A to element Z, we say element 0 to element 25. Would that be okay?
Yeah.
Okay. So now we look at a 32-bit integer that has, so what we need is 26 ones, right?
Yeah.
So we have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 16, 20, 24, 26.
There we go. Okay.
So now we convert it into hexadecimal. This is F,
That's
F, 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 F,
That's 3.
and that's the 3. But this also gives you an idea of, this is also a visual way to look at how elements are actually represented in a binary way. Is that okay? Cool. Okay. So, if you have any questions about this, you can ask questions about it. But without any further questions, I want to kind of move on and start to talk about. Well, maybe we'll get started with this one. Okay, we won't have enough time to actually finish the discussion, but we can at least get started with this one. So this is a new module that I am writing right now. So it's not entirely done, but it has enough stuff in it already. We talked about outcomes and events, blah, 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 blah. But instead of looking at all the boring stuff, let's look at the birthday problem. This class has approximately 40 people. And the question is, what are the chances that at least 2 people in this class have exactly the same birthday? That's what we are trying to figure out.
Down to the year? Down to the year?
Sorry?
Down to the year or just
down
dates?
to just the date. So you have 365 days to choose from, basically. So what do you think are the chances? So I'm not gonna, I will not read this. It's already on Canvas, so you can read about that. So what I'll do is I'm just gonna work out the problem, and you'll be surprised by the result, I think. Yeah, these are in fact music notes. My son was trying to print out some music sheets for his flute, except the printer was dry, so he wasted a few pieces of paper. I'm just reusing the paper here. Okay, so instead of looking at the problem as, okay, what are the chances of how many ways can we assign birthdays where at least 2 people in class share the same birthday, we'll flip it around and ask, what are the chances that everybody in this class has a unique birthday? There are no 2 people in this class share the same birthday. So we'll ask that question instead. Is that okay? Okay. So how many ways can we pick out, I'll call this 39 people in this class. So we'll say n equals to 39, which is the number of students in this class. So now I'm asking, out of 365 days in a year, how many ways can I pick 39 distinct birthdays?
So they're all different?
So they're all different. But the order is not important.
365 take 39. So
Choose, right?
yeah, choose.
Okay, so we are looking at this number, 365, choose 39. That's one representation of the combination or the number of combinations of choosing 39 out of 365. Okay, which turns out to be a pretty big number. Okay, all right, is that okay? So this is what we call an event. Okay, an event is basically just a set or a subset of all the possible outcomes. So we'll call this, the cardinality of f, which is the event of, tell me all the possible ways to assign 39 distinct birthdays to different people in this class. Okay, so out of 365 days. Is that okay? Distinct. So no two students in this class will share the same birthday. But each person can choose one out of the 365 days. Yep.
Wouldn't distinct events be permutation?
It is not permutation because I'm not assigning yet. I'm just saying, okay, pick 39 days out of a whole year. How many ways can you pick 39 different days from a year? So this is not permutation yet. So this is combination. Okay, so.
They could all be the same day, right? If it's combination, then they could all be the same day.
Nope, cannot be. It is without replacement. Combination is without replacement too.
Yes. Permutation is replacement.
Permutation is also without replacement.
Oh.
The only thing is whether the order matters or not.
Oh, order.
Yep. Okay. So we start off with this number, and then we say, so without any restrictions, how many ways can we choose birthdays for different people in this class? I do not need things to be different. I don't need them to be the same. I just ask, okay, how many ways can we have birthday arrangements in a class of 39 people? So the question is now saying, okay, you get to choose any one of the 365 days. You get to choose, guess what? Out of 365 days. And you get to choose any one of the 365 days. And we have 39 students, right? So the omega, which is the set of all the possible outcomes of all the experiments, has a cardinality of 365 to the number of the people in the class. It's a big number. It's a pretty darn big number here. Okay? But this f is not what we want. Okay? This f is actually the complement of what we want. Because this f is telling us how many ways we can have distinct birthdays with a class of 39, but what I'm really asking is what are the chances that at least two people in this class have the same birthday? Is that okay? So what we are looking for, what the probability that we are looking for is the set E with respect to the possible outcomes of omega. So E is omega minus f. It's just the complement of f. So in this case, this becomes the cardinality of E divided by the cardinality of omega. But since E is the complement of that, so now we have omega minus f, the cardinality thereof, divided by the cardinality of the entire omega. And so this is 1 minus the cardinality of f divided by the cardinality of omega. So let's figure this out, because I think the number will surprise you. So we'll go back to here and go to the share folder, and we'll create a new spreadsheet. Okay, so this is n, which is the number of students in class. It's 39, and the chances in this case is 1 minus, and then the cardinality of f. Okay. The cardinality of f is 365 choose or combine 365 choose 39, which is this n here, and then the whole thing divided by 365 to the power of the same number, which is the number of students, and it is 1.
Yeah, that's what I get too. I wish I had more decimal places.
Okay. That doesn't seem okay. Let's change this number to small numbers. Okay, 3, 4.
My CAS program gives me the same answer.
It's probably too big.
Yeah, it's so close to 1.
But that's not. This is not right. So I think I forgot something. Oh, I know I forgot something. I forgot one thing. Okay, I forgot to do this. This is not just come in. This has to be multiplied by the factorial of the number of people in class. Okay. The reason why that is the case is after I get the 39 unique days, now I get to decide, okay, who gets to get April Fool's Day, and who gets to get Valentine's Day, who gets to get a particular day. So I need to use permutation in that case to determine, okay, you get to get the first day, you get to get the second day, or the other way around. So that's why I was forgetting the permutation part, and that's why in this case, when you look at 39 students, the chances of at least 2 people having the same birthday within this class is still pretty high. It's a chance of more than 80% that at least 2 people in this class share the same birthday. And it doesn't seem to make sense, because if you think about it, there are only 39 people in this class. Actually, fewer now, okay? But there are 365 days in a year. So you would think that, hey, that's 9 times the number of people in this class, so that probability cannot be more than 1/9. But nope, the chances of at least 2 people in this class having the same birthday is actually more than 87%, which is not intuitive, it's counterintuitive. Okay, so we'll talk about this more on Wednesday, because this is an interesting problem to look at from several perspectives.